Hi, my name is Dan, and this video is one in quite a long series of videos which are charting the progress of using a digital simulator, so that simulates digital electronics, logic gates, and so on, and from there building up the things that we need to create a 4-bit CPU. Um, and as we go along, I'm trying to explain everything that's going on, because the point is not just to create this thing, which in its own right is fun, but also to gain quite a good understanding of the sort of things that go on inside a CPU and how they're built, or at least how this one is built, because, yeah, there's always going to be some specific stuff to the particular CPU that you're talking about. Um, so there's a roadmap of where we're going down in the description below. We're quite a long way through the process now, and we're just starting the last short series within the larger series of things. And this last playlist is we're getting to the stage where we're starting to put it all together, and we're actually going to hopefully at the end of this series have a working CPU. Um, the simulation software that we're using is called DigitalWorks. There's also a link to that down in the description below. But we're not going to see that in action in this video because we're about to launch into the final stage where we're going to actually put the CPU together. And so this first video in this shorter series within the larger series is a quick refresher of the architecture of the CPU and what we still haven't done and what needs to be done over the next few videos. So I've got up here a diagram of the CPU that I have designed. And if you've been following through, and I hope you have been following through, and if you've been with me from the beginning, then well done, because this has been quite a long haul. But if you've been following through, then you should understand what's going on here. But I will do a quick refresher as to what's happening. So the two black things are buses. So they're sets of wires that can be used for communication between components. Um, and there's a particular way that that needs to be done with a thing called output enable and a bus read on the components that can talk to a bus. There's a main bus on the left-hand side, and there's a specific bus on the right-hand side there that's called the op bus, and that's going to be used to get the opcode from the memory. We've got two memory banks, which are the light blue objects here and here, and one is for data and one is for the opcodes. This is a modified Harvard architecture, which I have cheekily called a Northumbria architecture, in that it uses one memory address register to access both of them, which in some ways may not be ideal, but we're very limited in the capabilities because having decided it's going to be a 4-bit CPU. We've also got a couple of registers. So memory address register is obviously a register. A couple of registers that hold the information that has been dragged out of the memory for use within the program. So there's the data register, which will hold information that's been brought out of the data memory, and the op register, which holds information being brought out of the op memory. The op register is connected directly to the control unit, which then, depending on what the operation is, will tell the other components what they need to do, and that's done by using control lines. And there's a whole lot of lines that aren't shown on the diagram because the control unit connects to just about everything. There is also the bit that can do calculations, which is the ALU. And then the ALU has a built-in register for the result of calculations, which is ALUX, but also has two registers in the main architecture called A and B, which are then hardwired into the inputs for the ALU. And finally, in terms of dealing with the flow of the program, there's a program counter, So the program counter is a special register which actually has two registers and does its own incrementing. Um, and we have yet to create that, so that's going to be the subject of the next video in this short series. And then finally, this thing at the bottom is the ring sequencer, which actually gives a sequence of signals which controls the fetch, execute, and increment cycle. And again, we haven't created that yet. It's not difficult, but that will be coming in a later video. So where we're going from here is we're going to create the program counter. We're going to create the ring sequencer. We're going to start putting stuff together. And then once everything's in, there are a couple of things that haven't been mentioned here that we really need. So one of them is if we need to be able to program this thing. So we need a mechanism uh, for being able to get information into the memory. And what we'll do is we'll attach some extra stuff to the buses that will just allow us to manually put in some values and store them in the memory before we get the computer to run the CPU. And then finally, we're going to need some control stuff. So I've just indicated that we're going to be able to uh, tell the CPU when to run. We also need to be able to reset it and to clear out the memory if we want to kind of get a really clear fresh start. And once we've got all that stuff in, we should be ready to actually fire it up and make it work. Touch wood that's gonna be successful. It's been quite a long set of things that we've made, and it's quite complicated. So be ready for there to be some problems when we get to that stage. I hope we're not going to have many, but there we go. So that's a quick description of the architecture of the CPU that we're creating and a quick description of what we have still yet to do. So let's crack on. That's it from me for now for this video. See you in the next video.